We have studied the upper bound, lower bound, and your tighter bound asymptotic notations. So this is a graphical representation, and we have here your x-axis and your y-axis. On the y-axis you have time, and on the x-axis is your size of the input. And your complexity increases with the size of the input for a given function n, and this is your big O complexity of your algorithm. For any function greater than n naught, we can see this graph. So with increasing the size of your input, your complexity is increasing, and f of n is your given function. It gives us the upper bound of a function which is c g of n for all n is greater than n naught. So now we understand this graph. We can say that f of n is O cg of n, which means f of n is smaller than cg n. So f of n is equal to big O n, for example, and this is your CGN algorithm. So if we consider the time complexity or the function f of n of a given algorithm, in the previous example we studied 2n plus 3 as a function f of n in terms of the input n, and another function called g of n for all input size greater than n naught, then fn is bound with the function gn with the multiple of some constant called c that we studied in the previous slides. Then we have your big omega notation, and we can say that running time is at least or the lower bound. So at max we can say it will take this much time, or at least it will take this much time, and we can represent your omega notation, big omega notation. So at least or a value greater than n naught size of the input for the time or complexity of your algorithm or time step required becomes 5n plus 3. We can say this function f of n is given, and the lowest bound that we can get for this algorithm is omega n, for n is greater than or equal to n naught here. Then we have big theta notation that we studied, which is the average bound. It represents the tighter bounds. So your function, we are given two upper bounds and the lower bound. So this is your lower bound, and this is your upper bound for example your f of 5n plus 3 function given like this. So we can determine the lower bound by a function c1 g1n gn, and c2 gn becomes your upper bound for that function f of n. So if f of n is theta g of n, then we say that there's a linear increase in your function f of n and g of n. And then if we say that the upper bound for the function is big O gn, we will say that f of n is not equal to omega gn of n. Given that, then we say that fn is asymptotically slower than your function g of n. So if f of n and g of n grow at the same rate asymptotically, we can write it like this. F of n is average case theta g of n. F of n is equal to, the upper bound is given, but f of n is not equal to the lower bound g of n, we say that f of n is slower than your g of n. And if f of n is not, if the lower bound is given and your function is not equal to, f of n is not equal to g of n, then we say that f of n is faster growing than g of n. So which notation should we use for representing our algorithm? Mostly big O notation is used. And why? Because it gives us the upper bound of the algorithm, how worst our algorithm can perform. So scientists are mostly interested to understand the maximum worst or upper bound complexity of your algorithm in terms of number of steps. So if we know the worst case, then we can improve it, and we can devise steps to update the algorithm to avoid it. So for the function, different functions that we are given, if it is 1, we say it is constant. Log of n means logarithm, n is linear. When n doubles in this n log n of n, then n doubles, then runtime slightly more than doubles, right? So n is multiplied by log of n. N squared is your quadratic and cubic is your n cube, and then 2 of n is your exponential function. So complexity of such algorithm, usually brute force algorithm that you will come across in the future, they would have the complexity of 2 of n. Here we have a graphical representation of our complexity classes. Here we can see for the input size and time number of steps. Time complexity means number of steps. So we have for a logarithm function, we can see it is very, time complexity is very low, even if we are increasing the steps quite large. For a linear, it is increasing in a straight line. For n log of n, we have a slightly curved, but the worst case in this case is cubic function, which gives us the worst complexity. So here is an example. I will give it as an exercise. Runtime is n factorial, and for if n is your 10 requires 1 second, so how many minutes are required to run your algorithm if we are given your size of the input? So look at the complexity, 200 centuries. Wow. So how can we analyze our algorithm steps? We see the constant statements, the initialization statements, how many loops are there, how many nested loops are there, how many sequence of statements we have, how many conditional statements we have. So we assess those to find the complexity of our algorithm. Simplest is one time. For example, array access requires only 1 time complexity. We know the index position, we can retrieve the data. This is an assignment statement. Arithmetic operations we have here. Then we have array referencing. You are getting the data. Array assignments, you are putting the data in this. For all j, you are putting 5. And you have conditional statements. These are some of the examples of your statements, and we already studied an example where this requires 1 time step. It will do at least n comparison, this will be executed n times because the loop is executed n times. And if we have c steps here in the statements, then they will be multiplied by n times because the loop is running n times. So your algorithm complexity becomes 1 from here. Then we have n minus 1. Comparisons multiplied by total steps here that we have. Then we have n minus 1 for here, and this one while loop. And so total complexity becomes a function of c is the number of steps within the list of statements here. So we calculate the total efficiency using the c steps that we have here, and it comes out to be 2 plus c multiplied by n minus c plus 2 plus 1, and we studied that we have to ignore the lower cases, low time complexities. So we ignore these and we ignore the coefficient that is being multiplied, and we only consider this complexity, which so the ON complexity is estimated for this example of code. So we have conditional statement, we have an if condition, we have statements. Statement 1 will execute ON time and statement 2 runs in ON squared time. We use a worst case complexity among all inputs, so because this has to be checked and then we go here. So what is the maximum running time? Because the second statement has a running time of ON squared, so the total complexity becomes the worst case complexity, which is ON squared. Again, we have an example here for recursive equations where we have a recursive function which needs a base case for the exit from the function, otherwise it will go into an infinite loop. So we have a base care. If this happens, then we are going to exit from this recursion. So if n is 1 here, small n, or we can say n is here, then it requires Tn is 2. However, if n is greater than 2, the cost of each step takes more time required by the power of, because we have to compute this again and again. If it is greater than 2, then 2 times it will execute plus t minus 1. For n is greater than 2, the complexity becomes this. So one method of solving the recursive functions and their time complexity estimation, you can use the iterative methods to estimate. So we use the back substituting, because when we have a recursive function, it calls itself, moves on, and then it returns to this previous step 1, step 2, step 3, first call, second call, third call, recursive call. So it moves here, then calls here, then we have the base condition fail, then we go back to the second call of the recursive call, then we return to the first recursive call. So recursive functions operate like this. So we are doing the back substituting. You can solve this using iterative method. So for previous example, when we have n is 2 greater than 2, so 2 n minus 1 was the case, 2, then it will go on, it will recursively call itself until we get a fail of this operation, which becomes 2n plus 2, and then when we fail, and then we substitute the values, back substitution, and total we get is 2n plus 2. That is our complexity. Here is another example of finding the estimation. So this is the first for loop, second for loop. It runs n times, it runs j times, so n squared. The complexity becomes for these two loops. Then we have ON complexity for this loop, and then we have for this summation